What if we could take the very gas that's warming our planet and turn it into the fuel that powers our world? It really does sound like something out of a sci-fi movie. But this is happening right now at the cutting edge of chemistry. We are talking about taking carbon dioxide, CO2, and flipping the script, turning it from a global problem into a seriously valuable resource. All right, let's dive right in.
So this is the big question, the one driving all of this incredible research. Can we really take CO2, the main bad guy in the climate change story, and transform it into the fuel of the future? Well, today we're going to unpack the science that's trying to make that a reality, and we're going to do it one fascinating step at a time.
All right, so here's our game plan. First, we'll look at why CO2 is such a tough nut to crack. Then, we'll meet the breakthrough catalyst that finally picks the lock. After that, we'll see how scientists build an assembly line to make fuel, and then, get this, how they can control what kind of fuel it makes. We'll peek under the hood at the secret chemistry, and finally, see how it all comes together to create sustainable jet fuel.
Okay, first things first, turning this problem into a resource. You see, the biggest challenge with CO2 is that it is just incredibly stable. It's a super stable molecule. Before you can do anything with it, you've got to understand why it's so darn difficult to work with. It's not just a gas floating around. It's more like a tiny chemical fortress.
And this quote from the research, it just hits the nail on the head. CO2 is a very stable, low-reactive gas molecule. The atoms inside are held together by these super strong double bonds, and breaking them requires a ton of energy. So think of it like a perfectly built, tightly locked structure. To get inside, you're going to need a very, very special key.
So, where do you find that key? Well, that brings us right to our second part, the discovery of a really special tool called a spinel catalyst. This, right here, is the first huge breakthrough in our story.
Now, this tool scientists use is called a catalyst. And if you're not a chemist, no worries. Put simply, a catalyst just speeds up a chemical reaction, but it doesn't get used up in the process. I like to think of it as a kind of chemical matchmaker. It grabs onto molecules, brings them together, and helps them react in ways they normally just wouldn't, or at least not without a lot of convincing.
So the scientists went on a hunt. They started testing a whole family of materials called spinel oxides, which is what you see here. And this table, it tells a great story. They tried a few different metals in the spinel structure. Magnesium and zinc, they were okay. Cobalt actually made methane, which is not what they wanted. But then, look at the copper-based one, CuAl2O4. It was the clear winner, just fantastic CO2 activation. And why? It turns out it had the most of something called strong basic sites, which are basically the perfect little landing pads for the acidic CO2 molecule to attach to and get pulled apart.
And just how good was it? Well, get this. The activation energy, that's the little push of energy you need to get the reaction started, was only 13.0 kilojoules per mole. Now that might just sound like a number, but for a molecule as stubborn as CO2, that is ridiculously low. It's phenomenal. This proved that CuAl2O4 wasn't just a good key, it was a master key for cracking open CO2.
Okay, so we've unlocked CO2. We're inside the fortress. But now what? Well, now we've got to build something useful out of the pieces. That brings us to part 3. The goal isn't just to break CO2 apart, it's to build it back up into long-chain liquid fuel. And to do that, you need a microscopic assembly line.
Here's how this tiny factory works. First, in step 1, our hero catalyst, the CuAl2O4, does something called the reverse water-gas shift reaction. That's a fancy way of saying it rips an oxygen atom off CO2, turning it into carbon monoxide, or CO. That's the demolition phase. Then, for step 2, a second catalyst gets tagged in, an iron-potassium catalyst. This guy is the construction crew. It takes that CO and starts linking it together to build long hydrocarbon chains, the very stuff that makes up liquid fuels. It's a perfect 1-2 punch, demolition, then construction.
And the results? Whoa, they were stunning. This 2-part catalyst cranked out liquid fuel at a rate of 429.4 milliliters per gram of catalyst per hour. That's a record breaker. This wasn't just some science experiment that barely worked. This was a high-performance engine for turning CO2 directly into fuel. Now, making fuel is amazing, but what if you could act like a master chef and decide exactly what kind of fuel you're cooking up? Well, that leads us to our next section, learning to control the final product by using hydrogen. This is where the science gets really, really elegant.
And the key to this fine-tuned control is a super cool phenomenon called hydrogen spillover. It's exactly what it sounds like.
Hydrogen atoms get energized on one part of the catalyst, the copper, and then they literally spill over to the other part, the iron, to get in on the action. Think of it like a relay race. The copper runner activates the baton, which is a hydrogen atom, and passes it perfectly to the iron runner to finish the race.
And here is the really clever part. Scientists figured out how to control this relay race. By treating the catalyst at a high temperature, they could make the copper and iron parts move further apart. This meant less hydrogen spillover, which resulted in more valuable chemicals called olefins. But with a low-temperature treatment, the copper and iron stayed cozy and close. That meant more hydrogen spillover, which produced more stable paraffins. They essentially created a dial to fine-tune what they were making, just by tweaking the catalyst's structure. How cool is that?
So, we know it works, and we know we can control it. But what is actually happening down there, at the level of individual atoms? It's time to peel back the layers and uncover the secret of the cascade reaction.
Okay, what you're looking at here are actual electron microscope images of the catalyst in action. It's amazing. On the left, that's what it looks like before anything happens. In the middle, after it's been activated, you can see these little copper particles have actually popped out of the main structure. And then on the right, during the reaction, a whole new material, iron carbide, is formed. This tells us the catalyst isn't just a static rock. It's a dynamic, shape-shifting machine that transforms to get the job done.
And those images reveal this beautiful, four-step chemical dance. Let's walk through it. First, when those copper atoms pop out, they leave behind little holes called oxygen vacancies, which are perfect docking spots for CO2 molecules. Then, hydrogen that's been activated on that copper spills over and converts the CO2 to CO. Step 3, that new CO immediately finds some nearby iron and transforms it into that active iron carbide. And that's the real engine that builds the fuel chains. Finally, the finished fuel molecule pops off, and the whole cycle starts over again. It's a perfectly choreographed, self-sustaining cascade.
And this brings us to the climax of our story. This is where all this amazing fundamental science gets put to the test to solve a massive real-world problem: engineering catalysts to create sustainable aviation fuel, or SAF.
See, to make high-quality jet fuel, you need specific molecules called aromatics. So the researchers added a second component, a zeolite, which is awesome at making aromatics. But it turns out how you arrange these two parts is absolutely crucial. When they just mixed them all together, they got the highest overall CO2 conversion, which is great. But when they set them up in two separate beds, something magical happened. The first catalyst made the building blocks, which then had to travel to the second bed, and this setup produced the highest amount of the exact aromatics they were looking for.
And the precision of that dual bed system is just incredible. Look at this chart. Over 95% of the aromatics they made were specifically C8 to C10 molecules. They weren't just making a random soup of chemicals, they were making exactly the high-value fuel they wanted, with almost no waste. That is atomic-level engineering at its finest.
So why does all this matter? Well, it's simple. Those C8 to C10 aromatics are basically the secret sauce for top-tier sustainable aviation fuel. They pack more punch, better energy density, and they improve the fuel's performance. This research creates a direct line from a single atom of carbon in a CO2 molecule all the way to a greener airplane in the sky.
Which really leaves us with one last, huge question to think about. As we get better and better at controlling chemistry at this fundamental, atomic level, what kind of future is that going to open up for us? I mean, from tackling climate change to designing brand new materials we can't even imagine yet, it feels like the possibilities are truly just beginning to unfold.